So as I mentioned, in sort of a conventional or traditional tracking approach, what you do is you build a model before something starts moving, right? So you might cut out a patch, find a contour, some method of describing the object. And then you do remember we talked about optic flow, where you essentially connect the dots. You do patch tracking with particles, which if you're in the OMS class, you did as a problem set. Or you might even solve some interesting complicated optimization problem. And then somehow you try to incorporate some invariance. So you might use edges because you know that those don't change a lot depending upon how the illumination changes, let's say. All right? But the problem is, if I'm going to track an object over an extended period of time, the object and the environment tend to change. And what I would like to do is I would like to not just track the object, but in some sense track the changes, incorporate the changes slowly as the object moves. So some work that we're going to talk about, and these are some slides taken from Yang, who did a piece of work that I'll talk about along with Ross et al. They took some inspiration from two places. First of all, Michael Black and Alan Jepson, way back in 1996, did something called eigentracking. So you guys know all about eigenfaces. Well, eigentracking was the same idea, but the idea is, so here we have Coca-Cola cans, and here we have these eigenimages. Oh, this one's a 7-Up can. How did that get in there? Okay, we have eigenimages of these different objects. And the idea was we're going to track this thing by finding places that we can represent well using those eigenimages. But one of the cool things they did was they said, you know, remember what didn't work so well in eigenanalysis, the eigenface, was the alignment. Things had to be aligned perfectly. Well, suppose we decompose the problem into the geometric part. That is, how is my object moving, maybe rotating, scaling, to what does it look like? Now, we've already seen this, right? When we were doing the good features to track, we talked, in fact, there was an image of a speed limit sign getting bigger and bigger and was being tracked, and the idea was it's the same image patch, it just deforms. Well, there they were using a single image patch. In the eigentracking, the idea was that we're going to look for a deformation, so it could be affine, could be otherwise, where we have translation, rotation, scaling, maybe even shearing. But now instead of just taking a single patch, we actually have a set of eigenvectors that describe the cocan. So for example, maybe if I rotate the cocan a little bit, or maybe some other change, I could represent all those different appearances. When they did it, it was done in sort of a nonlinear optimization way, but more importantly, they took a fixed basis set. So they took a whole bunch of images of Coke cans, created a basis set, and said, that's our Coca-Cola basis set. So we're going to need to do some improvement on that. The other inspiration here is also something that we've covered, which was particle filtering. Remember, Izard and Blake, instead of having a single proposal, the idea is you'd have a bunch of particles, and each particle would represent a possible location. And that allowed us to handle sort of non-parametric densities, right? Use a sampling-based approach. And there, what they were using were like contours, right? And they would propagate this over time. They would move the particles forward.